Welcome to EDU World Space.
What we know from this problem is that there are two conductive spheres of radii A and B, and the region between them are filled with some conductive material of resistivity ρ. And in part A, we're asked to show that the resistance between the two spheres is given by ρ over 4 pi 1 over A minus 1 over B. And the idea is to basically start with a thin spherical shell with a thickness dr, so that you can have a resistance of this spherical shell that's equal to dr, rho dr over A. So this is kind of like using R is equal to rho L over A, where dr is playing the role of L and the cross-sectional area is still the cross-sectional area. But what's happening here is that we're building the region between the sphere by these thin spherical shells by varying the radius from A to B. So we're going to sum up so we're going to pretend like we have little spheres here that fills the region starting with the radius of A and changing it by a very, very small increment dr, which is infinitesimal, all the way up to B, and we add all of those contributions, all of those little resistance up to get the full resistance between the two spheres. And the way to do this, the way you add infinitesimals, is by integrating. So we'll have to eventually do an integral, but let's now write the cross-sectional area, and that's nothing more than the surface area of the sphere. So dr then is rho d little r over 4 pi r squared, or I can rewrite that as rho over 4 pi r to the minus 2 dr. And then when I take the integral, I have the resistance is equal to, starting at A and going to B, rho over 4 pi r to the minus 2 dr. Now rho over 4 pi is a constant, so I can pull out of the integration, and then I'm left with integrating r to the minus 2 dr from A to B, which is nothing more than r to the minus 1 over minus 1 from A to B. And that's rho over 4 pi times minus 1 over B minus 1 over A. So then R is rho over 4 pi times 1 over A minus 1 over B. Or if I want to put, so that's actually the result that's desired. So now we'll solve part B of the problem. And in part B, we're asked to write the current density in terms of the terminal, in terms of the potential difference between the two spheres. So we know that the current density is the current over the cross-sectional area, and we also know that the potential difference is the current times the resistance, and we found this in part A. So we can solve this equation for the current. So the current is VAB over R, and then use this equation to eliminate the current over here, so that we have J is VAB over R, and times A. So I've just substituted for I into this equation. And we can write VAB, and I know that R I found in part A, rho over 4 pi 1 over A minus 1 over b times 4 pi r squared. And if we do some simplifications, so we can cancel out the 2 4 pi's. So I have VAB is equal to rho 1 over a minus 1 over b times r squared. And I could put this into put them under a common denominator. So 1 over a minus 1 over b, just so I can clean things up a bit, is equal to b minus a over ab. So if I substitute this into the denominator and shift things around a bit, well, let me just put it straight and then shift things around so it's clear what I'm doing. So I have rho r squared, b minus a over ab, and then I can move this to the numerator. So that's ab VAB over rho r squared times b minus a. So this is what they ask for in part B. Now let's do part C. And what we're asked to do in part C is to show that the result in part A, that the resistance that we got in part A reduces to equation 2510 when the separation between the spheres are small. It's small. So to define the separation as L, which is B minus A, and this thing is small, so it's much less than 1, or B and A are close together, right? So that would give you a small L. So another way to do that is to say, okay, well, A is close to B. So, and the other thing they said is that they give us equation 2510, which says that R is equal to rho L over A. So we have to show that the resistance we found in part A, which is R, rho over 4 pi, 1 over A minus 1 over B, which if we put it under a common denominator, we have rho B minus A over 4 pi AB. Now, the part in the numerator is already defined as L, so we have rho L over 4 pi AB. Now, when L is small, then A is approximately B, right? So if the separation between A and B is small, then the radii of the two spheres are close together. So A is approximately B. So then the product AB is approximately A squared. And so the stuff in the denominator, 4 pi AB, is about 4 pi A squared, which is the cross-sectional area of the sphere. So we end up with rho L over A, which is exactly equation 2510.